Okay, so today I am doing a session on section 2.2, which is all about functions. Functions is a concept that a lot of people struggle to understand. There's a lot of things involved. The biggest issue I see are with function notation, and so I'm going to focus on that, especially on things similar to what you would need to do on the assignment for this week. So 2.2 covers how to determine if something is a function. And for that, I recommend the vertical line test. I'm not going to cover that in this section, but I recommend doing that. And that's something you do via graphing. Covers function notation, using functions to model and solve real-life problems, which is what we'll be doing in the discussion. So I will. It's basically what we're doing this week, and actually in later discussions as well. And then evaluating difference quotients, which is basically the slope. It's just using different notation. So I'm going to be focusing on function notation in this session and under what a function is. So here's the definition of a function from the textbook. A function f. So we use the f just because it's called a function from a set A to a set B. So these are sets of numbers. So I'm going to, if I just have a set of values, and I'll just say, okay, all of my numbers are, I'll just make up some numbers. So let's say set A has 2, 3, and 4, and then B is 5, 6, and 7. So set A to set B is a relation, which means that there's just a relationship between them that assigns to each element x in set A. So A are the inputs, the x. So it assigns to each element x in the set A exactly one element y in the set B. So B is the outputs, which are the y's. So a function is a relationship between x and y. It's basically like an equation is a relationship between x and y. But what makes it specifically a function is that every input has only one output associated with it. So like if my input is 2, if I have x equals 2 and I plug that into the equation, and then let's say it gives me y equals 6, there's only one output there, so that fits. And so let's say 3 goes to 5 and 4 goes to 7. What makes it a function is that no matter what input you plug in, you always get only one output. That's what makes it a function. So if there is a case where you plug in a number for x and get 2 different values for y, it's not a function. There's only one output for every input that you plug in. So you're looking at inputs to outputs. You can have multiple inputs going to the same output. That's fine. But you just can't have one output going to multiple, or one input going to multiple outputs. So a function is basically a special type of equation. Not all equations are functions, but all functions are equations. So we can have functions for things that are not equations, but are situations, because it's just talking about relationships between things. So I've got 2 examples here where we're going to talk about the definition of a function and whether it makes a function or not based off of the definition. So example 1, let's say your input is the score in class as a percent. So let's say my possible x's, and I'm not going to list every possible score you can have in class, just a few of them. So let's say there's a 20%, somebody's awesome and has 100%. Let's say we've got a 76%. And then your output is the letter grade. And actually, you know what? I'm also going to put a 72% there. So let's say for our outputs, well, we've got A, B, C, D, and F as our possible letter grades. So if I have a score, if I have a 20%, well, that's an F. A 100% is an A. 76% is a C, and a 72% is a C. So if I have a 20%, well, that's an F. A 100% is an A. 76% is a C, and a 72% is a C. So if I have a score, if I have a 20%, well, that's an F. A 100% is an A. 76% is a C, and a 72% is a C. So if I have a score, if I have a 20%, well, that's an F. A 100% is an A. 76% is a C, and a 72% is a C. So every score has only one letter grade associated with it. And so that makes it a function. Because if you know what your score is, you know what your letter grade is. Because there's only one possible choice there. So that's a function. Now, example 2, we're going the other way around, where your input is your letter grade and your output is your percentage. So in this case, our input is the letter grade. So your choices, A, B, C, D, and F. And then you could have potential different percentages. I'll just use the same numbers as example 1, although really there's lots of choices. So if you have an A, okay, well, that can go to 100. B doesn't go anywhere. C goes to 76 and 72. D doesn't go anywhere, and then F goes to 20. So those actually go to C. In this situation, if you know what your letter grade is, that doesn't mean you necessarily know what your exact percentage is. So if you have an A, technically you could have anything between 90 or 89.5, because we round up, 89.5 to 100. So there are lots of possible outputs that match with an A. In this specific example, a C has 2 potential outputs here, 76 or 72. So there's 2 choices, and you can't say for sure which one is the one you have, basically. So that makes it not a function, because there are multiple possible outputs. Some relationships are functions in both directions, and that's special, and that's something called one-to-one, but not all relationships are. So this is one where it's not a function in both directions. It's only a function if you have a score and you go to the letter grade. You can't use your letter grade to predict what your exact score is. So a function is, the concept of a function is a lot about your inputs and your outputs, what the relationship is, and whether you can get an answer from an input, basically. Is there a specific answer you can get out? And that's what a function is all about. And of course, since we're in math, we're going to be looking at functions that are, equations, but the concept of a function is something that applies to other different fields. And computer science has functions all the time. Their functions are basically where you give it some inputs, it does a whole bunch of stuff, and then you usually output something. So that's using a function. So the concept of a function is used in many different fields. So in math, we have what's called function notation. And so it's f parenthesis x parenthesis. This is read out loud as f of x. So that's how you read that out loud. This is not f times x. This is special notation. And so the way to know the difference is to recognize what your input variables are in the use, the context. Generally, we don't write multiplication of variables with a parenthesis like that. If we were to multiply, we'd write fx. So fx means multiply. But if it's f parenthesis with x, that's function notation. So context, notation, the difference between the notation and the symbols, that really matters. So function notation, if you see something using that notation, that tells you automatically it's a function. And what's in parentheses is your input, so that tells you where you plug in numbers. And then you've got basically the name of the function or the output here. So most of the time we use f, but you can use names. You can use letters to mean things like h for height. And then you just indicate your input. Your input is usually x or t for time. And so it's a special type of notation that just tells us that we have a function. So when you have function notation, you can use that to find function values, the value of a function. and that is basically means finding the y value, or finding y. So you will be given an input, an x, and you're finding what the output is associated with it. So if you're finding y, the key here with function notation is that f of x is the output, so it is basically the same thing as y. So if you have an equation with a y and it's a function, you can replace y with f of x. So when you're finding a function value, you're finding the y value, plug in for x, and then you're following the order of operations. And generally, when we have things that are in function notation, f of x equals is what it looks like, so you only have to do stuff on the right. The other thing you do with function notation is solve, and if you're going to do that, you're going to replace your function notation with y, or whatever y equals. So sometimes you're plugging in numbers. Oops, it's not always 0. Sometimes you plug in numbers for y, and then you solve for x. So you can solve or find function values, which is called evaluating. And the key is that f of x and y are interchangeable when you have a function. So example 1 here, this is something similar to what you would do in problem 1 on the assignment, where you are evaluating a function. You're plugging in things, and those things may not be numbers. You may be replacing them with variables. So our function is f of x equals 2x plus 5. So just think of that f of x as y. When we have f of 2, that 2 in parentheses is telling us that we're inputting 2. And that function notation tells us x is the input. So that means you are replacing x with 2. So this happens on both sides. You replace both sides of that equation with, 2 for x. I'm going to just kind of highlight that so you can see. So everywhere you see x, you replace it with 2. And then you evaluate only the right side with function notation, because it's not f times 2. It's function notation. So don't touch that left side if you're evaluating. We only simplify the right. So 2 times 2 is 4. So we have 4 plus 5, and that gives us 9. So f of 2 equals 9. And that is giving us an ordered pair, because it's telling us our input, our x is 2, and our output is 9. So an alternate way is to write it as an ordered pair. We use function notation because if somebody just said x equals 2 and you're evaluating, you're finding y, you would get an answer of y equals 9. And that answer doesn't connect back to what number you plugged in to get 9. Function notation tells you what number you plugged in, and so it gives you more information. And so it's preferred when we have functions, because it gives you both the input and the output, not just the output. Now, the one in the middle here, the example in the middle is f of a. So again, that's telling us our input is a. So that means that x is now equal to a. So it's a way to switch variables. So everywhere I have x, I now write a. And then you would simplify if possible. But those are not like terms. So you can use function notation to switch variables without really changing anything. So it allows you to, instead of always using x and y, you can just change variables if there are ones that make more sense. Now the third one over here, we have t minus 1 is our input. So that means that's the entire input. So x is equal to t minus 1. So everywhere I see x, I'm going to replace it with t minus 1. And now on the right side, I need to simplify. So I need to distribute. So that's 2 times t, which is 2t. And then 2 times negative 1 is negative 2. So I have 2t minus 2 plus 5. And then negative 2 plus 5, that's 3. So f of t minus 1 is 2t plus 3. Now, the purpose you might want to do that, you might want to plug in something instead of x, but plug in an expression like t minus 1 might be if you're changing, if you're doing like, let's say you have an equation and it is in metric and you need to convert it to US units. If you know the relationship between the metric unit and the US unit, you can use that relationship to plug in the function and what the new unit would be looking like, and then that would give you the equation in US instead of metric. So you can use it to convert between different types of measurements. That's one option, one way you can use something like this, and why you might plug in t minus 1. Like, let's say I have something that's measured in, let's see, what do I know? I know, I think 1 inch is 2 point, well, I know that, let's see, I'm trying to think of a good conversion that I know. I think an ounce is 28 grams. So let's say you have something measured in ounces. If you want to convert it to grams, then 1 gram is 1 over 28 ounces. So you would plug in for ounces 1 over 28 and then maybe g for grams. And that would be allowing you to convert your equation from something with ounces to something with grams. So that is an option, and one of the reasons why we use function notation is we can do that sort of conversion without having to write a whole new equation. You're just plugging things in, and you can see what the relationship is with what you plugged in. So, do you have any questions on this slide? Okay, so moving on to example 2. So this is another one where we're evaluating, and here we have a piecewise function. So I wanted to show what happens if you have a piecewise function, because you're plugging in for x, but you need to figure out which one of the two you plug it into. So the first one we have f of negative 2. So x is negative 2. So if we look at our piecewise, if x is less than negative 1, you use negative 3x minus 3. If x is greater than or equal to negative 1, you use the other equation. So this is sort of like an if-else situation. If this, then do this, otherwise do this. So that's something that you might see in computer programming. Often you write programs where you have a function and you're given an input, and then you perform different things based off of what that input is. So this is an example of the kind of thinking that you would have to do in computer programming. So x is equal to negative 2, and that is less than negative 1. So we need to use the top equation, the negative 3 minus 3. So when I show my work for this, I pretend that I just have that top equation, because that's what's relevant. That's the one I look at because my x is less than negative 1. So now I need to follow the order of operations. So negative 3 times negative 2 is 6. So I have 6 minus 3, which is 3. So f of negative 2 is equal to 3. Third one, or the one in the middle, we have f of negative 1. So our two choices are x is less than negative 1 or x is greater than or equal to negative 1. So since x is equal to negative 1, we want to use the bottom equation there because that's where we fall into. So f of -1 is -1 squared, and you have to use parentheses there when you plug in negatives so that you square correctly. And then plus 2 times -1 and minus 1. So I'm only evaluating the right. So -1 squared is 1. 2 times -1 is -2, and then minus 1. Then 1 minus 2 minus 1 gives us -2. So f of -1 is -2. Now, on the right, I have f of 1. So 1 is greater than or equal to -1. So I am using that bottom equation again. So f of 1 is 1 squared plus 2 times 1 minus 1. And I'm only working on the right side. So 1 squared is 1, 2 times 1 is 2, minus 1, 1 plus 2 minus 1 is 2. So I got f of 1 equals 2. So when we're evaluating, all we're doing is plugging in for x and then working the order of operations. The important part is knowing the notation and that you don't do anything on the left. You're not dividing by anything because it's not multiplication. This is a notation, a specific function notation, so we're only working on the right side. Are there any questions? Okay. Now this is similar, this example is similar to what you would see on the homework, and we're going to be doing this again next week. It says find the zeros. So we have talked about zeros. We talked about zeros, I believe, both week 2 and week 3. So zeros are the x-intercepts. But we include complex numbers in case that happens. So if you get anything in imaginary, then it's still a 0. It's not an intercept, but it is a 0. So x-intercepts are where y is equal to 0, which in this case, because we're using function notation, that's where f of x is equal to 0. So if you see anything saying find the zeros or find where f of x equals 0, you're finding zeros or x-intercepts. So f of x equals 0 means that you're replacing f of x with 0. So you are solving for x, because the zeros are always x values. So if I subtract 4x from both sides here, I get -4x equals 6. And then I'm solving for x. I get x equals -6/4, which I need to reduce. So I can divide the top and the bottom by 2. That's -3/2. So that is the 0, or the x-intercept. So when it says find the zeros, you're basically setting your equation equal to 0. You're setting the function equal to 0. So the f of x part is not the important part. It's what it's equal to that's important. Second example here, I have a quadratic, x squared minus 6x minus 16. So f of x is just the y value. What we care about are the x's. We're finding the zeros, so we're setting f of x equal to 0. You're setting your equation equal to 0. So now we're solving a quadratic equation, which is using the techniques from 1.4. So I believe this is one that factors. So I have x times x. And let's see, 8 times 2 gets me 16. If I have a -8, +2, that's -16. -8, +2 gets me -6. So that's going to be what it factors to. Those multiply to -16, add to -6. So now I set each factor equal to 0. And then I solve each one for x. So I get x equals 8, x equals -2. And so those are my zeros. The zeros are only where y is equal to 0. 0 does not mean x equals 0. It's not a y-intercept. It's the x-intercepts. So if it says to find the zeros or to find the x where f of x equals 0, you're finding the x-intercepts. So you're looking for x. Are there any questions? Okay, so that's all I had for today, because the big thing was using function notation, seeing how it's used, understanding what things mean. The rest of the sections that you're looking at this week are all going to be about graphing functions. So it's just like graphing equations. So you're going to be using Desmos a lot, and there will be some looking at function notation. And so I recommend looking at the handout in the weekly content about function transformations, because that will give you some guidance there. 2.6 and 2.7 use function notation a lot. You're going to be plugging things into functions. So I recommend attending my live session at noon on Sunday, where I'm going to do function combinations. So if you're struggling with functions, that's one you want to see. Definitely be there. And then Monday at 6 p.m., I'm doing one on inverse functions. That's another one that you're going to want to be at if you're really struggling with functions, because that will give you more examples of how you work with functions. So hopefully I will see you at those two. And I hope you have a really great weekend. Happy Friday, and hopefully I'll see you on Sunday. So, bye.